Alright, what's up everybody? Today I'm going to go over logarithms. This is the third video in the COVID series. It's just still chilling in quarantine right now. And I got nothing better to do than make some math videos, so today we're going over logarithms. Um, you got a little bit of a joke here. We got the music that math teachers dance to. It's a logarithm. Got him. Oh God. Okay, now that's out of the way. Uh, the basics. So a logarithm, it's the inverse of an exponential function. We'll get into that in a minute, but that's just kind of what you have to know just to get us started. It is just like an exponential function. It has the same properties on graphs, but it just does the opposite. That's what the inverse is. So the goal of a logarithm, or like why we use the logarithm, it's to solve for an unknown exponent. So if you know a base, and you don't know an exponent, and then you know the final answer, then that's what you use a logarithm to find. There's two different types of logarithms. You have common logarithms and natural logarithms, which we use e. Um, Common logarithms are pretty frequently used in, the algebras, geometry, even pre-calculus. But then once you get into calculus, it's almost all natural logarithms, and then complex math is natural logarithms. So in this video, I'll mainly be talking about common logarithms. I'll go into natural logarithms a little bit at the end, but I'll do a whole separate video if people want me to do that on natural logarithms. These guys will get crazy once you get working with just complex math. So exponents. So in order to understand logarithms, it is critical that you have a solid foundation of knowledge on exponents. So this is going to be a refresher. If you don't know exponents already, I'm planning on making a video on that in the future about exponents, and just straightforward. It'll be a short video. But here's a quick refresher. So we have x to the first just equals x. We got x to the second, or x squared, equals x times x. Yeah, x to the third, which is also known as x cubed, equals x times x times x. We could go on forever. X to the fourth would be x times x times x times x. Basically, you're just multiplying the same number however many times it tells you to by itself. For example, we have 3, right? 3 to the first is just 3, to the first, it's just 3. 3 squared is 3 times 3, which is 9. We have 3 cubed is 3 times 3 times 3, which is 27. So that's just general exponents. You got to be able to do that if you're going to want to be able to do logarithms. And let's go into logarithms. So we're going to go into common logarithms. This is the format you're going to see for a common logarithm. You're going to see all of the similar variables over here, and I'll explain the arrows here in a second. This is how I was taught to do it. How I remember these, because these can get a little bit tricky to remember, is I just think about it. I use what my teacher calls number sense, which is I know the goal of a logarithm is to find this variable. It's to find x, right? We're going to know b and we're going to know y, but we want to know what x is, right? What's the exponent here that it'll be unknown, and we're going to try to find. So that is why x goes on this side equal sign, right? It's like 2 plus 2 equals what? That's what we're trying to find. We're trying to find what 2 plus 2 equals, right? We're trying to find what x is. We're trying to find this exponent. So it goes over here. Now, as for how to remember this, b is the base over here. It's the base raised to the x power equals y. So it's the base here, and it's the base here. Y is just going to come right over on the other side of the equal sign. That's how I remember it. The other way to remember it is doing it with these arrows. So instead of saying it like you're going to read this kind of like a sentence. So you're going to say b to the x equals y. You can also say it here, b to the x equals y. Same thing, b to the x equals y, b to the x equals y. Either one of them works, just preference based on the person. So let's try one right here. If we have 2 cubed equals 8, right? Log of 2 of 8 equals 3. 2 to the third equals 8. Bam, done. Another one. 3 cubed equals 27. 3 to the third equals 27. Easy. That's what a logarithm is. So now I'm going to get into a little bit of examples. So what power does 4 have to be raised to in order to equal 64, right? This is the question it's asking. What power does 4 have to be raised to? So what is x so that 4 to the x equals 64? Now there's two different ways to do this. There is the guess and check method, which I'll show you first, which is how I would do it. And so that's how everybody will do it until you learn logarithms, which is right here, right? 4 to the first equals 4. Not quite there. Got to get a little bit bigger. 4 to the second, 16. Still got to get a little bit bigger. 4 cubed equals 64. Nailed it, right? 4 to the third equals 64. 4 to the what equals 64? 4 to the third equals 64. X is 3. So that is the guess and check method. The other way you can do this is write out your logarithm. So you have log of 4 to the x equals 64. 4 to the x equals 64. X equals 3. You can get this by typing it into your calculator, which I'll get to in 2 slides, I believe. But it's just real quick. You type this in your calculator, it spits out 3. Easy. The reason that you'll want to be able to do this is because not everything is going to come out to be a perfect and beautiful number like 3, right? Sometimes you're going to get crazy numbers because everything's not going to go into the whole numbers and be pretty like I like math to be. It's not going to be like that. It's going to get pretty wacky, just like this next example. What power does 2 have to be raised to in order to equal 57? Here's what this one's asking. 2 to the x equals 57. What is x? Well, let's try our guess and check method. Well, 2 to the first equals 2. Duh. 2 times 2 is 4. 2 times 2 times 2 is 8. 2 to the fourth is 16. 2 to the fifth is 32. Oh, we're almost there. 2 to the sixth is 64. Wait, we overshot it. What is x? I don't know. I know it's between 5 and 6, but who knows? It's anybody's guess where that could be. That's why you have to do logarithm. Log base 2 of x equals 57. X equals 5.833. And that's just the number your calculator will spit out. And that's how you do it. Done. 2 steps. Instead of guessing and checking, freaking out, and failing the test. So here's how you'll do this. I only know how to do this on TI-84 Plus Texas Instruments because that's the calculator I have. I have this guy right here. A bunch of my buddies have this one. It's the same thing. If you do have a different calculator, the only thing I can tell you is just experiment around. Eventually, you're going to find something. All calculators will be able to do this. But if you have one of these, and I suggest if you don't, that you get one because they're extremely useful, especially with graphing functions. You're going to go over here and press this guy right here. It says math. Over here, it's on this one. It says math. You're going to scroll down until you see this. It'll be log base. And then you're going to want to scroll over that and highlight it. You're going to select it by pressing enter. And it's going to come up with this equation that looks exactly like the equations we've been doing. And it'll just have blanks. It'll have blanks. There'll be a blank right here. And there'll be a blank right here. So for this one, you'd put a 2 into the one with the parentheses right here. And you put 57 into the big blank on the main part of the logarithm. And you just press enter. And it would tell you 5.833, and it would go on forever. And that would just tell you, bam, solved it, done. That's all you have to do. Plug it in your calculator, it spits out a number. So the next thing I'm going to get into is what if there's no base? So what if it just looks something like this, right? Log 1,000. Well, there's nothing here, so what to the what equals 1,000? That could be anything. Well, if you have something like this, it's assumed it's going to be 10. So if you don't see anything here, it's assumed that it's log base 10. Kind of like if there's two things in an equation and they're both in parentheses and they're right next to each other and there's no symbol, you just assume that you're multiplying. It's the same thing. If there's nothing here, if there's no number here for the base, you assume that the base is 10. So this would be 10 to the x equals 1,000, just like this. And we can solve that easily. X equals 3. You can do that either you can plug this in your calculator, or one of the cool things you can do is if you have a log base 10 and then a number that's divisible by 10, you can just count the zeros. So if it was log of 10,000, x would be 4. If it was log of 100,000, x would be 5. You can just count the zeros, but that's only if it's log base 10 and something divisible by 10. So for this one, x is going to be 3. So for example, something like this. If you just see this on a test, right? Log 39, literally 5 characters right here. And they want you to just says solve. Well, you're going to put it in like this. Log base 10, because it's assumed, of 39 equals x. And don't freak out because it's not going to be a whole number. It's still the same thing. 10 to the x equals 39. You can plug it in your calculator right here. you're going to get x equals 1.59. So, as with anything, there are exceptions. We have our special case number 1. This is if log of literally anything, any number, pick a number and put it right here, except for 0 and 1. It has to be bigger than 1. So 2, 3, 4, 5, 6, 100,000, 200,000, a million, 5 million, 10 million, anything. And then with a y of 1 equals x. So just like this, anything to the power of x equals 1. There is an exponential rule that deals exactly with this thing. In order to get 1 out of an exponential function, the exponent has to be 0, right? So 10 to the 0 equals 1, 11 to the 0 equals 1, 12 to the 0 equals 1, 13 to the 0 equals 1, 565,000 to the 0 equals 1. So if there's any number to the x equals 1, you know that x is 0. Done. Done with the whole problem. You could have something like this. Log base 100 of 1 equals x. Well, what would x be? Well, in order for you to have 100 to the x equal 1, x has to be 0. That's just properties of exponents. What if it's something like this, right? Log base 598,329, and then a 1 equals x. Well, this number to the x power equals 1, x has to be 0. Easy. It's the same thing. So that's our special case number 1. If you have log of anything right here and then a 1, x has to be 0, because the only way for you to get 1 is if the exponent is 0. Special case number 2. Log of anything again, and then instead of having a 1 right here, you have 0 or a negative number, right? It's the same thing as right here. You have a 1 right here. Well, now you have a 0 or a negative number. It is not possible to solve this logarithm. And I'll explain that here in a second, but this is where it kind of gets a little bit tricky. So for this equation, x does not exist. The reason for this is 3 to the x equals 0. What power are you going to raise 3 to that's going to equal 0? You can't. 3 to the first power is 3. 3 to the second power is 9. 3 to the 0 power is 1, right? We just talked about that. That was our special case number 1. 3 to the 0 power is 1. So what power can you raise 3 to be so that it equals 0? There isn't one. There's literally not a number that you can do that. It is impossible. 3 to the whatever power equals 0 is impossible. If you type this into your calculator using the method I just talked with the press the math button, scroll down to log base. If you type this in your calculator, it's going to say domain error. And the reason is because there is no domain, right? Domain is the x values. That's another way to say the x values. Domain error. That means, yeah, there's no x values because there's literally not a value that can solve this function. Another one just like this. Let's say you have a negative number. 2 to the x equals negative 8. Well, what exponent could you raise 2 to be a negative number at all? You can. 2, let's say you had 2 squared, right? 2 times 2. Well, that's 4. 2 cubed. Okay. Well, 2 times 2 times 2, that's 8. 2 to the 0, we already talked about that again, it's 1. Even if you have 2 to a negative exponent, that just means you get a fraction. It's impossible for you to raise something to an exponent and end up with a negative number. So if you have a negative number right here, x also does not exist for now. If I get any of my pre-calculus buddies watching this, and you guys want me to do a video about imaginary numbers, let me know in the comments. I can do one about imaginary numbers. For everybody else that's watching that's just laughing like, oh my, no, I remember this, from second grade, no numbers imaginary, numbers going forever. Well, there is a thing called imaginary numbers, and just real briefly, I'll do a separate video on this later probably, but it's a number that scientists kind of came up with and mathematicians came up with to represent this x does not exist. It's kind of like an excuse because they want to put something there because we hate writing down x doesn't exist, right? It has to be something. And there is a way using imaginary numbers that you can get this answer. But for now, this is super important. For now, x doesn't exist. There's no way, there's no number you can raise 2 to in order to equal a negative number. There's no power you can raise 2 to equal 0. This last one. This is a common mistake I saw people fall into. But as soon as they see a negative number, boom, x does not exist. But that's not true. if you have a base that's negative, you can still get an answer, right? Negative 4 to the x equals 16. Well, negative 4 to the second power equals 16, right? Negative 4 times negative 4, that's 16. That comes out to be positive. So if you have a negative number down here, that's okay. But you cannot have a negative number where the 16 is, right? Log of anything, it can be anything down here. But up here, it's if it is 0 or a negative number, it's not possible. But if it's negative down here, perfectly fine. This can be a little bit confusing. And if you have any other questions on a specific problem, you can always let me know, and I'll help you out. So finally, I'm going to talk a little bit about natural logarithms. So natural logarithms except the base, yeah, so it's a normal logarithm except the base is e, which is Euler's number. Uh, a lot of people will recognize this from calculating compounding interest for banking firms and banks. They'll use this number. It is approximately 2.718, but the decimal does go on forever. It's an irrational number. I honestly have no clue how it's found. I don't know the equation for how you get Euler's number. I don't know why they use it in banks. All I know is that it is the base in the logarithm, right? So it's where this negative 4 is right here. It'd be log base e of whatever. So when e is the base in logarithms, it's considered to be a natural logarithm. Again, don't know why. E is extremely useful in calculus. Again, that's why I said at the beginning of the video, I'll just be touching on it at the very end, but mostly you're going to focus on common logarithms. Natural logarithms, very, very useful in calculus. We use it all the time. Yeah, and natural logs are represented by ln. I have literally not the slightest idea why they chose ln. To me, it doesn't make any sense. My only thing is maybe, Yoda was in charge of the math department that day, and it was natural log. But I honestly couldn't tell you. But yeah, so if you see ln and then a number, all that means it's base e. Kind of like how if you just see log and then a number, it's assumed the base is 10. Same thing. If you see ln, it's assumed the base is e. And that's going to do it for logarithms. Again, if you have any specific questions or have a problem, feel free to leave them in the comments. I hope I answered any of your questions. If you want me to be more specific on any certain parts, I'd be happy to do that. Yeah, stay safe during the pandemic, and I'll check you later. Adios.